Here we've got a female with a triplet litter. It's a very rare sight to find triplets in the fall time. One of the cubs is a runt of the litter. It's not likely to survive. 20 years ago, it wasn't all that uncommon to find triplets in the fall. About 5% of the bears we caught, or females with cubs, had triplets. We're seeing triplets born in the spring, but we're not, one or more of those cubs is not making it through to the fall. We're seeing reductions in cub survival, things of that nature, all related to climatic warming.
The ice is now melting 3 weeks earlier each year. That means that there is 3 weeks less feeding time for pregnant mothers.
Once they come ashore and the sea ice melts, the bears are forced to fast for anywhere from 4 months for most bears, up to 8 months for a female such as this bear here, who would have come ashore last summer and has not had a seal meal since last July.
If the current warming trend continues, the future looks bleak for polar bears. This remote part of Patagonia is one of the coldest places on Earth outside the polar regions. Glaciologist Dr. Stephen Harrison has been working in locations like the Neff for 20 years. He's been studying how they've changed over that time.
The Patagonian icefields are the most dynamic icefields on Earth. To understand climate change in the southern hemisphere, we need to go to places like this. It gives us a very good record of climate change over the whole range of timescales. The ground I'm standing on, that glacier, the Neff Glacier, was here in about the 1870s. And by about the 1930s, it had retreated to this shoreline, the lake shoreline. And since then, since the 1930s, of course, it's retreated another 2.5 to 3 kilometers, perhaps 2 miles, back up its valley. When we were here in 1998, this whole lake was completely covered with icebergs. It was so thick with icebergs, we could hardly get our boat to the ice front. And yet that's all gone. That landscape has completely changed now.
The rate of that glacier melt is now accelerating. In southern Greenland, the amount of ice flowing into the sea has doubled in the last 10 years. This is slowly but steadily causing sea levels to rise. "8,000 miles away, the inhabitants of the tiny Pacific islands of Tuvalu are already facing the realities of an invading sea. As temperatures rise, so do those of the sea, causing oceans to expand. And that, coupled with the glacier melt, means that sea levels will rise even higher. Earlier this year, tides rose to their highest level ever known, flooding the homes of the islanders. But warming seas don't only mean rising seas. They have other implications too. In August 2005, Hurricane Katrina struck the coastline of Louisiana, Mississippi, and Alabama. It was the most destructive hurricane ever to reach the Gulf of Mexico. It created a storm surge that ravaged 100 miles of coastline. Was it the high sea temperatures that made Katrina so intense?
typical hurricane starts as an atmospheric disturbance over Africa, but it's here in the Gulf of Mexico that they grow to their full destructive power.
Hurricane expert Greg Holland has been investigating what fueled Katrina's force.
The process requires that the oceans be warmer than about 26 degrees Celsius. The tropical clouds that get the hurricane started draw the energy from the surface high up into the atmosphere. And by this means, the ocean heat energy is used to fuel the development of the immensely powerful winds. And it is so powerful, it could run the entire electric grid of the United States for several weeks. The really destructive winds are in the region just outside the eye of the hurricane. And these are so strong, they shred the surface of the ocean into a morass of sea and spray that becomes so thick that it literally becomes impossible to tell the difference between air and water. And the warmer the tropical oceans, the more destructive the hurricane can become.
When Hurricane Katrina breached the levees of New Orleans, sea temperatures in the Gulf of Mexico and the Atlantic were the highest ever recorded. In the United States, the intensity and sheer destructiveness of the hurricane became the turning point in the debate about global warming. 2005 was the worst season ever recorded. And Greg Holland is one of those who believes that worse is yet to come.
As you can see, there's a massive rebuilding program underway, but unfortunately this stretch of coastline will certainly be revisited by hurricanes like Katrina, and because of global climate change, they're going to be more intense, more destructive, and possibly more frequent.
It's a grim warning. But is global warming and the changes we're now seeing really a new phenomenon in the Earth's history? These days, when we talk of climate change, we tend to mean changes that we ourselves have brought about. But of course, the climate of the Earth has always been changing, either because of some great cosmic event, like a collision with a meteorite, or else because of some more slower, gradual change in the amount of energy that the Earth receives from the sun. It's the sun that provides our planet with warmth and light. But the amount of energy that the Earth receives from the sun varies. In cycles of tens and often hundreds of thousands of years, the Earth tilts and changes its orbit around the sun. And with each cycle, the patterns of light energy playing on the Earth changes. These natural changes have contributed to dramatic shifts in our climate. In the time of the dinosaurs, it was much warmer than it is now. You would have found dinosaurs roaming in forests close to the North and South Poles. 70 million years after that, much of our planet was freezing. It had become locked in a cycle of successive ice ages. If the city of New York had existed 160,000 years ago, it would have been on the edge of an ice pack some 2 kilometers high. And yet global temperatures were only 4 degrees lower than they are today. 30,000 years later, the same city would have been under 5 meters of water. Yet global temperatures were less than 2 degrees warmer than they are now. This seesawing in the Earth's climate was driven by natural forces long before mankind appeared. But there's another powerful influence on our climate that we have to take into account. Among the many gases that make up the air we breathe, there is one that is particularly important: carbon dioxide. It traps the sun's energy and so keeps the planet warm. Greenhouse gases, like carbon dioxide, act as a blanket around the Earth, preventing the sun's energy from reflecting back into space. It's called the greenhouse effect, and it's prevented the planet from freezing since the Earth began. Without it, the global temperature would be minus 19 degrees Celsius. On the face of it, carbon dioxide seems to be a good thing. It stops our planet from freezing and so sustains life on Earth, and without it, no plant could grow because they need carbon to build their tissues. Leaves absorb the gas from the atmosphere through their pores. They then break down the carbon dioxide molecules, release the oxygen, and retain the carbon. Over hundreds of millions of years, the great forests took so much carbon dioxide out of the atmosphere that they reduced the greenhouse effect and cooled the planet down. When the trees died, they were buried, and over time crushed and compressed with the carbon still within them. In the ages that followed, these layers were slowly buried beneath the Earth's surface. At this open-cast coal mine in China, you can descend for 500 meters through layer upon layer of rock representing tens of millions of years. Right at the bottom lies a layer of what was once wood and leaves and is now coal and shale. When I was a boy in the 1930s, the carbon dioxide blanket was still below 300 parts per million. This year, the thickness reached 382, the highest figure for hundreds of thousands of years. Every year, the blanket is getting thicker. But how can we possibly know that carbon dioxide levels are higher now than they were thousands of years ago?
You can see the ice here is absolutely full of bubbles, and the bubbles were formed when the ice was formed. And of course the bubbles contain atmosphere, oxygen and carbon dioxide. If we want to understand the role of carbon dioxide as a thermal blanket over the Earth, we need to know about how carbon dioxide has changed, the concentrations have changed in the atmosphere over hundreds of thousands of years. An analysis of bubbles such as these in places like Antarctica and Greenland gives us that fantastic record.
These ice cores have been extracted from as much as 3 kilometers beneath the polar ice caps. And for Professor Marc Serres, each one provides a valuable source of information about a particular moment in the past.
Well, this particular chunk of ice is about 16,000 years old. It comes from the Greenland ice sheet. What we see here are layers of fossil snow. Every year on the top of Greenland there's an accumulation of snow, and this gets compacted year through year, layer after layer of snow, eventually to form these layers of ice. And it's within these layers of ice that we can tell all kinds of things about the Earth's past. What we find today is that the carbon dioxide concentrations in the atmosphere are higher than anything we've seen in the past 600,000 years. It's telling us that human activities are having a strong impact on the climate system. And if we measure this in parts per million of carbon dioxide in the atmosphere, what we call the pre-industrial level, before humans were starting to have an impact, was around 270, 280 parts per million. What we see now, the most recent records today are telling us that it's up to about 380 parts per million. So you can see that today's levels are far beyond anything that we've seen in the past. If you talked to me 5 years ago, I would have been kind of a fence sitter on this whole idea of greenhouse gases involved in climate change. No more. The changes that we've seen seem to be much too strong, much too radical to be just simply explained by natural climate cycles. What we're seeing now is the impact of humans. Humans are starting to change the climate itself. That's what we're seeing today.
It's here at the Met Office's Hadley Centre in Exeter that we can find the answer to some of the big questions. This supercomputer can perform 10 billion calculations per second, each one contributing to a model that scientists like Peter Cox can use to predict our future
Climate models essentially have come out of weather forecasting models. They're run for much longer periods, they're run for hundreds of years rather than days, but they contain all the complexity. They contain clouds, they contain rainfall patterns, they contain winds, and climate models also have to contain slower components like how the vegetation and the soil respond to change and how the oceans change.
The model is like a virtual world, a sort of flight simulator, where everything from the melting ice in the Arctic to the formation of clouds in the atmosphere and the temperatures of the oceans are represented by formulae. It can give us the probability that future events may happen. For instance, what are the chances of our having another major heat wave like the one of summer 2003? And as the planet warms up, can we expect heat waves more often?
It's impossible to put any particular climatic or weather event down to climate change alone. But what you can do is say that climate change affects the chance of an event occurring. And the very extreme 2003 summer we suffered in Europe and killed many people in France, for example, is a case in point. That's something that is a rare event now. It's a 1 in 200 year type of event. But that is twice as likely as it was before we started to change the climate. And by 2040, because of future climate change, it will become a 1 in 2 year event, almost the norm. By 2080, we'll consider that a cool year.
They factor both natural climate variations and our carbon dioxide emissions into their model to see which best explains the changes in temperature over the last 120 years. The key question, of course, is how can we distinguish between variations due to natural causes and those variations of the climate that are induced by human activity? And the key thing that convinced me, at any rate, was a graph like this one that we marked out on the floor that had been prepared from climate scientists like Professor Peter Cox. Now, explain to us the significance of this graph.
Okay, what we're going to do is to take a walk through time. And the first thing to note as we walk through is that the climate is naturally variable. It's a spiky beast. Occasionally there's a downward trend that's associated with a volcano going off that cools the system down because of the dust it throws up. But generally it just oscillates around. And then we get to a period around about 1910 where you can start to see an upward trend, a warming of the climate, a global warming if you like. And the issue is, what caused that? Was that humans or was that natural? So what we do to try and work that one out is to take a climate model and to put in the various factors. And what we can see with this green curve here is a climate model that includes just these natural factors. So this is when volcanoes go off and the output from the sun. And you can see that the green curve can reproduce reasonably well this mid-century warming. So up to this point, you could reasonably argue climate variation can be explained by natural factors. But as we move on, we can see that's no longer true as you get to the latter part of the 20th century. From about 1970 onwards here, you can see the red curve, the observed temperatures, and the green curve really beginning to diverge. And the question again is, what caused this recent warming? So we run the model again and we include human factors. Particularly we include the greenhouse effect, mostly from carbon dioxide that comes from fossil fuel burning. And then we get this yellow curve, and we can see, as well as reproducing the mid-century warming, we get this recent, rather rapid warming reproduced. And that tells us two things. One is that the model looks realistic, it looks like the real world. And the second thing, the model tells us that this recent warming is due to human beings.
So there you have it. There seems little doubt that this recent rise, this steep rise in temperature, is due to human activity.